So chemical equation, right? Chemical equation, guys, is pretty much a short-on way of writing your chemical reaction. It involves reactants and products, in which reactants are normally on the left-hand side of the equation and your products on the right-hand side. Always use the A and B analogy. That is, if A and B is supposed to react, it's going to produce C and D, where A and B is what we term as our reactants, right? And C and D is what we term as our products. Now, in understanding balancing equation, you need to understand the different types of reaction that you can actually have. So let's look at the different types. We have about 4 or 5 different types. The first one that we're going to look at is decomposition reactions. Now, a decomposition reaction is one in which you have one reactant, right, that is now decomposing into 2 or more products. So, for example, if I'm supposed to have something like calcium carbonate, right, carbonates tend to decompose into its oxide and carbon dioxide. So you're going to get calcium oxide plus CO2, right? On that note, it is important for you guys to know as well at this level that nitrates, right, tend to decompose to its oxide, right? Oxygen, that is, oxide of the metal, as well as nitrous oxide. So, for example, if you have something like magnesium nitrate, that is MgNO3-2, right? Then what you're going to form is magnesium oxide, NO2, right, plus oxygen. However, for species that are very stable, like sodium and potassium nitrate, are very difficult to decompose. So salts of sodium and potassium decompose into sodium nitrite, so it decomposes into its nitrite and into oxygen. And the reason for that is because it's too, the bond between the sodium and the nitrate, right, it's too strong. So as a result of that, though, it's going to take too much energy to overcome what we term as the lattice energy that is actually holding the ionic structure. All right, good. So that is decomposition reaction. Next one that we're going to look on is neutralization reaction. Now, at your level, they might tell you that neutralization reaction is when an acid and a base react, but that's not always the case. A neutralization reaction is one in which water is often formed. So if you're looking on reactions in which carbonates reacting with an acid as well. All right, so neutralization reaction. So if I have sodium hydroxide react with HCl, it's definitely going to form salt and water. So this is sodium chloride plus H2O, right? So we have decomposition, we have neutralization. We're going to now look at combination reactions. So combination reaction is one in which we have 2 reactants that combines together, right? Normally under pressure. So if we have sodium react with chlorine, that's going to form sodium chloride. So it's 2 single entities that are now just reacting with each other. So that's your combination reaction. Then we have what is known as displacement reaction. Everybody have this off? Because I'm moving quickly now. I remember we have a lot of topics to cover. Talk to me. Remember, you can open the mic and talk. It's an interactive session. We have all this decomposition, neutralization, combination. All right.
Yes, sir.
Seeing some thumbs up. Don't afraid to talk, you know, guys. All right. So might not get a session like this again. I didn't introduce myself, right? All right. So I'm Mr. Hudson from Hudson's Tutoring Services, chemistry educator and chemist by profession. All right. All right. So let's go. So we're now looking on displacement reaction. Now, displacement reaction, as the name suggests, it's basically displaces a species from the next. Now, it's based on a reactivity series. That is, you have a reactivity series for metals and you have a reactivity series also for non-metals. The reactivity series, by now, everybody's supposed to know, right? It's based on a mnemonic, which we said, please send cows, monkeys, and zebras in 2 large heavy cases, mark stamp foods per shovel. So that is please, K for potassium, Na for sodium. Please send cows, monkeys, and zebras in 2 large, heavy cases, mark, stamp, goods, perishable. Let's go through that. Potassium, sodium, calcium, magnesium, aluminum, zinc, iron, tin, lead, hydrogen, copper, mercury, silver, gold, and platinum. What this is saying to us is that elements that are actually higher up in the reactivity series will displace species that are lower in the reactivity series. So let's look. Oh, slow down. Oh my God, I'm going too fast. Whoa. For real?
So are you going a little bit too fast?
I'm going too fast? All right, I'm gonna.
Yes, sir.
Sir, can you please slow down?
Moving God's speed. All right, let me slow down for you guys. All right, I'm gonna slow it down for you guys. Yeah, my sessions are normally very high pace, but don't worry, right? Because my students are normally on a certain level. But I understand. All right, so let's go. You lost like a bat. Shalicia, don't worry, man. I'm here for you. All right. So what I'm saying here, I'm gonna take it slow, is that we have displacement reaction. Let's think about it. I always use this analogy. So I'm gonna use Javid Atkinson. So Javid is a swag boy, right, over here in Trinidad. And Javid comes and says, hey boy, you know, I'm gonna take that girl from you. You know, so what? And you have, what's another, give me a name for a guy here. I'm using Azar, right? Azar is my Jamaican Bridget, right? Azar is my Bridget. And then Javid walks across Felicia. So I'm using some names from the class. And Felicia and Azar, you know, are together. And Javid probably swag and him have things and all of that. So Javid no displaced displaced Azar from Felicia. It's the same thing that actually occurs here. Now, species that are higher up in the reactivity series, right? They are way more reactive than species that are low. So as a result of that, when they are in a given reaction, they will displace these species. For example, if I'm supposed to react potassium, right, with zinc sulfate, what I'm saying here is that potassium, because it's higher in the series than zinc, right, it's competing with the zinc for the sulfate. So it's the same way Javid and Azar will be competing. So because now Javid is a swag boss and I'm a person, so Javid is potassium, right? So it's gonna displace Azar with zinc, right, from zinc sulfate. I hope Azar is not here, and I hope Jada don't tell Azar. Good, right? So that's gonna give us potassium sulfate, right? That is K2SO4 plus zinc. Everybody understand what's going on there regarding to displacement reactions? All right, good. See, Chalicia, you said it lost like a bat, now your phone like a rat. All right, so let's go. So that is your displacement reaction. You also have displacement reaction when it comes on now to non-metals. For example, non-metals reactivity increases going up the group. Therefore, fluorine is more reactive than chlorine, which is more reactive than bromine. I think my camera stops. Just check. All right, good. So I'm back. So fluorine is more reactive than chlorine, which is more reactive than bromine, which is more reactive than iodine, which is more reactive than astatine. So let's look at an example. Let us say that we have fluorine reacting with potassium iodide. So it's the competition of the non-metals now, right? Fluorine, because it is higher than the iodine, is going to displace potassium from the iodine. So you end up with potassium chloride plus iodine gas. Iodine in solid matter. All right? Fully understand that? You guys can take it a bit slow enough. All right, good. All right, so we'll finish with combination, we'll finish with decomposition, we'll finish with displacement. We're going to now do what is known as double decomposition. This is the last one. So once you understand these reactions, then balancing equation comes a little bit easier for you, right? So let's now look on double decomposition reactions. Now, double decomposition reaction is when you have two salts reacting and they simply exchange their ions. So, for example, if we have sodium nitrate reacting with zinc sulfate, right? What is going to take place? Sodium is going to exchange position basically with the zinc. So you get sodium sulfate, Na2SO4, plus zinc nitrate, which is ZnNO3, bracket 2. That is pretty much it. All right. Now, I think someone mentioned before, the charges of ions and all of that, right? And it is important for you to know how to write a chemical formula when balancing equations. So let's just run through that. Oh, you know the charge on a species. Well, the charge on a species is based on the overall atomic structure of the species. Remember, right, that you have what is known as electronic configuration, right? So let's just use magnesium, for example.
Excuse me.
Yeah, go ahead.
You're still going fast or even faster than before.
I'm going fast or fast?
Yeah, for real.
All right, no problem. Let's try to tone it already. Let's try to tone it on. All right, let's go. All right, so I was mentioning about it, the charges and the ions, right? It is important for you to know the charges and the ions. Why? Because that is the way in which you know how to write a given compound. Let's use magnesium, for example. Now, the charge on a given species is based on the number of valence electrons that are there. So it is the valence electrons that really give a particular atom its charges. What's the valence electron? The valence electron tells you the amount of electron that is in the outer shell of a given atom, right? So, for example, magnesium, the atomic number is 12. Persons who know about atomic structure already know that for neutral species, that is species that are not charged, right? The number of protons is equal to the number of electrons. So I'm basically trying to do two topics in one. I'm now teaching you, so I'm teaching you chemical balancing equation, but at the same time, if you don't know how to write a compound, don't make sense. So I'm teaching you now how to write compounds. And at the same time, in teaching you how to write compounds, I'm also revising atomic structure. So I'm showing you how everything come about. So magnesium atomic number is 12, proton number is there for 12. For neutral species, the number of protons is equal to the number of electrons. So the atomic number is 12, that is equal to the proton number. Kishana, go ahead.
Sir, what's the last product?
Again?
What's the last product?
What's the last what?
The product there.
The last product, zinc nitrate. Say that no, 3 bracket 2. Zinc nitrate, man. All right, good. So the number of protons is equal to the number of electrons. So what does this mean, class? It means then that magnesium has 12 electrons. Now, based on the octet rule, we want to distribute these 12 electrons in what we call shells. The octet rule said the first shell must hold 2 electrons. So I'm teaching atomic structure at the same time. So first shell must hold 2 electrons. Second shell can hold a maximum of 8 electrons, right? And the third shell, at this level for you guys, hold a maximum of 8 electrons. In some texts, it might say 8. That is because when you start to go to subatomic orbitals, when you reach K, all right? But don't worry about that. We're going to use this. So what we want to do now is to distribute these 12 electrons based on the octet rule, right? So we're trying to distribute the 12 electrons right here based on the octet rule. So the first shell holds 2, right? That leaves 12 from 2 or 2 from 12, whatever way you want to say, right? Leaves 10 electrons, good. The second shell can hold a maximum of 8. So why not put 8? 2 plus 8 is 10. We still have 2 electrons to be distributed, right? So the last shell holds 2. Its electronic configuration is 282. Now, this is our baby right here that we're focusing on. The electrons in the last shell. Now, metals tends to have 1, 2, or 3 electrons in the last shell, while non-metals will have 5, 4, 5, 6, or 7 electrons in the last shell. The overall purpose now of bonding and forming a compound, right? Is to be stable. So all these metals and non-metals want to be like your nearest noble gases in the periodic table. Now, the noble gases that we have helium, whose electronic configuration is 2. Everybody following me so far? All right. While keeping up?
Yes,
How
sir.
about good students?
No,
Everybody
sir.
keeping up? Who's not keeping up? Going too fast for you still?
Sir.
Yes, sir.
All right, don't worry. Soon start upload some video, you can purchase them. All right. So helium. So I have helium right here, whose electronic configuration is 2. Right. Then we have our master, which is known as neon, whose electronic configuration is 2,8. And then we have argon, whose electronic configuration is 2,8,8. So magnesium come now and say, you know, I want to be like my nearest noble gas. The nearest noble gas to magnesium is neon. Neon is 10, right? Magnesium is 12. So neon, so magnesium with electronic configuration 2,8 to so 8. But you know, if I lose 2 electrons in my valence shell, I would be like neon. So why am I gonna do that? Right? I have to do that. So lose the 2 electrons now, and losing electron, remember that electrons are negatively charged. So if you lose negative entities, Victoria, if you lose negative entities and you stop bad behavior at school and all of that and misbehave or whatever, right? Then obviously you're gonna be more positive, don't? Make sense, Vic? Make sense? Where's Victoria? You know, engage with me, man. She's gone. All right. So of course you're gonna form magnesium that is Mg2+. Right? So you get a charge of Mg2+. So that's how you get the charge. Similarly, if you have something like chlorine now, right? Chlorine, whose electronic configuration is 287. Chlorine is a non-metal, so it will gain an electron. So when you gain an electron, you want to gain 1 electron to be like argon, that is 288. Right? So gain an electron to be like argon, whose electronic configuration is 288. All right? And hence the charge here will be Cl minus. Everybody good? Everybody good so far?
Yes, sir.
All right, excellent. So we're learning, man. So this is why I know when I put something on the board. All right, before I even say that, let me talk to you guys about radicals. So we're learning formula writing, everything in one. Do you guys prefer the light to be on or off? I don't matter which one.
On.
On. All right. Good. All right. So let's go. We have what are known as radicals. Now, radicals are charged species. You don't need to know the definition. So radicals are charged species, right, that are formed from the combination of 2 or more atoms. So, for example, we have monovalent radicals, like NH4 plus, charges NH as this plus right here, right? We also have stuff like OH minus, which is the hydroxide radical, right? What else we have? We have sulfate radical, SO4 2 minus. We have the carbonate radical, CO3 2 minus, right? What else we have? Popular one. We have the nitrate radical, NO3 minus. We have the phosphate radical, PO4 3 minus, right? Good. So these are all radicals. Now let us try to write a formula for a compound. Calcium phosphate, right? So calcium phosphate. By now, you guys should know the electron configuration for calcium, which is 2882, right? Hence the charge on calcium is 2 plus. It's 2 plus, right? Remember that when you're talking about the charges, right, the number comes before the symbol. But when you're talking about oxidation state, the symbol comes before the number. Don't get it twisted. All right, good. So calcium is Ca2 plus, and then phosphate, PO4 3 minus. Now, when we're writing formula, guys, we do what is known as valence switching. Right? It's a simple method. which will basically switch the valences and allow it to be entities. Huh? No, well, I thought everything was correct, but if it is the number of modes that you're trying to find, just give me a second, guys. If the number of modes that you're trying to find, what you definitely need to do is apply a 1.6 times 10 to the 24 over 6.02 times 10 to the 23 and get the number of modes. Probably just a miscalculation that was done there. All right. Good. All right. All right. Where are we now? Sorry about that. All right. All right, good. All right, so calcium phosphate, as I was mentioned before, right? What you need is valence switching, right? So valence switching is what is actually gonna be taking place right here. Now, this would give us, this is what I mean by valence switching. So the 2 plus here is gonna come down here as an entity, while the 3 minus is gonna come down here as an entity, right? Because we want the charges to basically balance out. So this is saying to me that I have 2 calcium, I have a calcium with a 2 plus charge and a phosphate with a 3 minus. So I can use a valence switching method, or I could also use what I call the LCM approach. So using the valence switching method is quite easy because this would give me Ca3, right? PO4, bracket 2. Why I put a bracket? Because remember that a radical is 2 or more atoms. So I want to group them to show that, guess what? The charge is distributed over all of the species. That's pretty much it. Now, I could also do another method, which we call the LCM approach. The LCM approach is where I'm trying to balance the charges. So I have 1 2 plus charge and I have 1 3 minus charge. The LCM between 2 and 3 is what? 6, right? 2 goes into 6 3 times. So obviously calcium is 3, right? 3 goes into 6 2 times. So PO4, 2. So this is saying to me that I need 3 calcium and 2 phosphate to balance the charges so that the charge equates to 0. Oh, what's the name? Hudson's tutoring. The first time you're hearing of us? First time? All right, good. Everybody's good so far?
Sir, can you repeat, please?
All right, so what I was saying to you. All right, give me a second. All right, what I was saying to you is that we can do both methods, which is valence, which is the easier method, youngster, right? So the charge on calcium is 2 plus, the charge on the phosphate is 3 minus. So all you need to do is just switch the valences. So the valence is now going to become an entity, right, for the number of atoms. Hence why it's a Ca3, PO4 bracket 2. All right, good. We feel like we're comfortable in writing compounds now. We need to go on. You know? So I teach you just a while ago electronic configuration, how to write compounds, the formula for compounds. Now, can we go to balancing equation and finish up?
Favorite.
What's that?
I said it's my favorite.
I didn't hear that.
My favorite.
Oh, it's your favorite. Okay. But I'm asking, can I go on now to balancing equations? I want to hear from Mass. Oh, give one more example. All right, no problem, man. All right, one more example. Let's look on sodium sulfate. All right, you guys are going to help me with this one. So sodium is Na, right? Sulfate, SO4 2 minus. What's the charge on sodium? What do you think is the charge on sodium? What's the charge on sodium? 11, no man. You're mixing up charges and atomic number. You need Hudson's, man. So look at this now, youngster. So sodium is 11. That's the atomic number. Therefore, it's 11 protons and 11 electrons. I want you to know, I think that was Felicia. I want you to know to use the octet rule, Felicia, right? To tell me the electronic configuration of sodium. Based on the octet rule that we discussed, what would be the electronic configuration? How much electrons would be in the first shell, first shell? Based on the octet rule. What's that?
281. It will be
All
2
right,
then
281. Excellent. So because electronic configuration is 281, what is this saying to us? That we can what? We can lose one electron to become stable, right? Good. So what will be the charge now if you lose one electron? What do you think? Just like how magnesium loses 2 electrons and it was 2 plus, what do you think is going to be the charge here?
1 plus.
Excellent. You're learning, man. So 1 plus. But normally we don't need to put 1 plus. You can just put plus, all right? Because it signifies that the charge is a 1. All right, good. Valence switching would give us any 2 because it's 2 plus here. Oh, must not showing. All right, no problem. Let's correct that. Good. So valence switching will cause the 2 to come here. So we get any 2 is to the 4, right? Remember it's 1, so it stays as it is. So any 2 SO4. Understand?
Yes.
Good. All right. So we're looking good. All right, let's continue. All right, so we're comfortable with electronic configuration. We're comfortable with writing formula. Let's now go to balancing equation. Now, the purpose of balancing equation is a seesaw mechanism, right? It's a seesaw mechanism, meaning then that you don't want the pot to fall off the seat despite pot being heavier than him. So what you want to do, you want to load the seat in such a way that there is some amount of equilibrium that is established, right? So it is always in balance, pretty much so. Right? Let's look at it. Now, theoretically, you might have a lot of persons that give you steps and guidelines of the balance equation, but pretty much what you need to know is that you need whatever the amount of atoms on the left-hand side of the equation, you want the same amount on the right-hand side. That's all, right? There are some guidelines, yes, that you can follow, right? You might not necessarily have to follow them if it is that you reach at a particular level in chemistry where you are now comfortable. All right, let's look on a equation here. So we're looking on magnesium reacting with hydrochloric acid. So this is an acid reacting with a metal. For those who don't know, when an acid and a metal reacts, form salt and hydrogen gas. So in this case, right, magnesium, and this is also a displacement reaction. Remember, magnesium is highly reactive series than the hydrogen, right? Right? Everybody remember that? That I did when I just started the session?
Yes, sir.
All right, excellent. So it's magnesium chloride, which is MgCl2, right? Reacting with hydrogen, so that's MgCl2 plus hydrogen gas, right? So that is actually what's going to form. That's it. So we get MgCl2 reacting with hydrogen. Let's balance it now. So when we're balancing equation, we start off normally with balancing the substance that occurs one time in a compound, meaning that it's only occupied once in a compound, either on the left-hand side or on the right-hand side. So if you look here, magnesium is on its own here, but it's occupied only one time over here. So we can balance that first. You realize it's one magnesium here and one magnesium here. Now, oftentimes, we put numbers in front of these, which we call coefficients. So the coefficients, and when you start with mole concept, it's basically telling you your stoichiometry. It's the amount of moles that are now reacting in the equation. All right, good. So this is saying to us that 1 mole of magnesium reacts with 1 mole of HCl to produce 1 mole of MgCl2 and liberate 1 mole of hydrogen gas as it is now. Right? This is not balanced as yet, so let's try to balance it. So it's 1 magnesium, right? Good. On both sides. So we don't need to balance that. That's balanced. Let's now move on to the chlorine, right? So in some instances, persons will actually leave oxygens for last, right? But you don't necessarily have to. But sometimes you will see persons do that. All right, good. So it's magnesium wrapped with HCl, right? And that forms magnesium chloride and hydrogen. All right, good. So on the left-hand side, place a 2 in front of HCl. All right. So on the left-hand side and on the right-hand side, you're seeing 1 mole of magnesium. Let's look on the chlorine now. On the right-hand side, this is 2 chlorine, right? On the left-hand side, we have 1 chlorine. So we can put a 2 in front of the HCl, right? Putting a 2 in front of the HCl, let's just check the hydrogen if it's balanced. So it's 2 hydrogen, right? And it's 2 hydrogen here. Now, a rule of thumb for you guys, and you need to know this, is that when you're writing your equations, there are some things that you need. 1, you need to balance the equation, right? 2, you need to put the state symbols. That is, is the species solid? Is the species liquid? Is it aqueous? Or is it a gas? Now, for you to know that, right, you definitely would need to study your solubility table for salts, for some salts, that is. But let's just run through quickly the solubility table of salts, right? All chlorides are soluble, right? Except for what? Silver and all chlorides are soluble except for silver and. So we don't know the solubility table. What's going on?
Gold.
Silver and gold?
No.
Lead, sir.
Lead. So all chlorides are soluble except silver and lead. So I'm giving you the solubility table, right? All carbonates are insoluble except for sodium, potassium, and ammonium. So right for me. So we're giving you the solubility table. So ready? Let's go. All chlorides are soluble except for silver and lead. Yes, Britt? Quickly.
Sir, saying hold on.
Huh?
Hold on.
Hold on. All right. Hold on. Remember, I said we have a lot of topics so we want to go through now.
Start, sir.
And they decide not to come to a class. So we have to just give them at a high speed because we've been to tell them to come to the sessions. Come to our sessions, it's effective. So I want to give them a lot as possible and I can in the short space of time. You know?
Sir, I can start.
Let's see. That's why I have to actually move at that pace. But let's go. So all chlorides are soluble except lead and silver. All right. All carbonates are insoluble except sodium, potassium, and ammonium. So all carbonates are insoluble except for sodium, potassium, and ammonium. Same thing for hydroxides. All hydroxides are insoluble except for sodium, potassium, and ammonium. So all sodium, potassium, and ammonium salts are soluble. All right, so we're definitely gonna have a next session for accounts next week, probably around Sunday. All right. You guys having problem with understanding what I'm saying when I talk? And I'm seeing somebody saying in the group. I'm not sure if it's me. Anybody? Yes, Kishana, go ahead.
Sir, can you repeat the last sentence you said?
All right, so I was saying that hydroxides, all hydroxides are insoluble except for sodium, potassium, and ammonium. Everyone can understand when I speak. I'm not sure if there's any language barrier. All right, because I'm actually looking the group now. I'm not sure if that was directed at me or something. I'm not sure. So we're all good? Everybody understanding? All right, good.
Yes, sir.
Kishana, obviously I'm not talking about you guys. All right, cool. All right. So we said that all hydroxides are insoluble except sodium, potassium, right? Barium hydroxide and calcium hydroxide now are sparingly soluble. So you can add that. That's barium hydroxide, BaOH bracket 2. Barium hydroxide and calcium hydroxide are sparingly soluble. Right? So I gave you guys carbonates, I gave you guys hydroxides, I gave you guys chlorides. All right.
So,
All right,
so
so
what is the sign for
go ahead, Michaela.
hydroxide and calcium hydroxide? What
I'm not hearing you.
the sign?
What's that?
The symbol.
Oh, the
You know,
symbol,
like
hydroxide, OH.
Sir, I don't think you gave oxides.
Okay.
Did you give oxides?
Why am I hardly hearing you guys? Go ahead, Rihanna.
Did you give oxides, sir?
Oh, oxides, no. All right, so all oxides are insoluble except potassium, sodium, and calcium oxide.
Say, can you repeat oxides, please?
What's that, Felicia?
You can repeat this with oxides, please.
All right, so I'm saying that for oxides, all of them are insoluble except potassium, sodium, and the calcium oxide. And as you know, all nitrates are soluble. All right, all nitrates are soluble. And the sulfates now, all sulfates are soluble except lead and barium sulfate. All right, everybody have that?
Yes, sir.
All right, good, good, good. All right, so let's write the state symbols because CXC, when you go on the CXC exam, all right, they're marking you not just for the balance equation that you have, but the complete marks. You'll get the complete marks when you actually have the correct state symbols. So magnesium here, being a metal, is definitely solid. That's so one, right? So magnesium is solid here. This is HCl, this is aqueous, this is an acid, right? All chlorides are soluble except lead and silver. This is aqueous, obviously. Hydrogen is a gas, so this is G. All right, good. So we said that this is balanced, right? Everybody agree that this is balanced? Can get full marks for it?
Yes, sir.
Chalicia, why you keep on being negative and speaking negative over your life? Why? Talk to me. Why are you saying that there's no hope? Why? There's power in the tongue, my friend. There's power in the tongue. Be careful what you put out there in the universe. There's always hope. Stop doing that, man. All right. You're not the first person that might be struggling in chemistry. I got a student last year, 3 days before the exam. No, nothing in the exam, nothing in chemistry before. He enrolled with me. I've been for 3 days straight. Got a grade 1 straight in profile. You're at this point, you're at what, 1 month out? 1 month and a couple weeks out from the exam? That's a lot of time. All right, good. Let's try one more example in terms of balancing. All right, and then we'll go to ionic equations. All right, let us see what we have. Calcium reacted with water. This is gonna give us calcium hydroxide, all right, plus hydrogen gas. Right? Tell me what I need to do to balance in this here. So I have 1 calcium on either side. That's 1 calcium on the left, 1 on the right. I have 2 hydrogen here. Well, I have 4 hydrogens on the right hand side. I have 1 oxygen here and 2 oxygen on the right hand side. What do I need to do? So I want to get equal amount of each substance or each atom on either side. All right, go ahead, Felicia.
Put a 2 in front of the hydrogen and the oxygen.
Put a 2 in front of the hydrogen and the oxygen. So you mean put a 2 in front of the water. This right here?
Yeah.
Excellent. All right, so if I put a 2 here, you realize now that the left-hand side also have 4, right? Just like the right-hand side, and the number of oxygen will also be balanced. All right, good. Everybody comfortable? Think that we kind of understand how balancing works?
Yes, sir.
All right, sounds good. All right. Shalicia, seems like you have some hope now.
Yes, sir.
All right, stop doubt yourself. All right, we're gonna move on now to ionic equation. Right? Ionic equation. Now, ionic equation is really where we're trying to show what forms our ionic product at the end. It's showing us the spectator ions that we have, and there's a certain rule that we apply. The first thing that we want to do when looking at ionic equations is write a balance equation. Right? So the first thing is to write a balance equation. Once you have written the balance equation, you want to now move to the second step, which is breaking up the compounds into ions, meaning the constituent ions that make them up. The first rule, write a balance equation. Second, right? You want to break up the compounds into ions. That makes it up. But be careful. When we're breaking them up into ions, we only can break up aqueous species. As remember, they are aqueous, meaning that they are able to dissolve in a solvent. Hence why we can break them up. So for substances that are solid, we don't need to break them up. Neither for gas, neither for liquid. And obviously, we can't break them up for solids. All right, good. Once we have broken up these ions, right, the next step is to eliminate what we call a spectator ion. But what's the spectator ion? Just like watching a football match, the spectator ion are those that whose state symbol remains unchanged on either side of the equation. That is, if on the reactant side it was solid and on the product side it's solid, right? They will eliminate them. We call them spectator ions. So that's your next step. Once we have eliminated our spectator ions, right, we rewrite the equation with whatever species are left behind. All right, let's put this to practice. Give me a second. Let me just reply to some messages. All right, so we're looking on lead nitrate reacting with sodium chloride. You guys gonna guide me through this one. So it's lead nitrate, PbNO3 bracket 2, right? Aqueous, of course, reacting with sodium chloride, NaCl aqueous. This is a double decomposition reaction. I hope you guys see the different type of reactions. So this is now gonna form what? Lead chloride and sodium nitrate, right? So PbCl2, because lead is 2 plus, all right, which is solid, PbCl2 solid plus, what's that? Sodium nitrate, NaNO3 aqueous, because all nitrates are aqueous. All right, balance the equation for me. Someone talk to me. Oh, bear in mind, before I forgot to mention, if you have a radical, right, we treat radical as a single entity. So this is a nitrate radical, and we have 2 nitrate radicals here on this side, and on this side here, we only have 1, right? So we just simply need to put a 2 here. So I'm not gonna balance it for you. Put a 2 here, right, to balance it. So we don't necessarily, once we have a radical, we don't necessarily need to split up the individual atoms there. What I mean by this, you don't need to say, okay, this is 6 oxygen on this side, and this was 3. No, it's a radical, so we treat it as a single entity. So it's okay, this is 2 nitrate radical, and this is 1. So I need 2 nitrate radical on this side as well. Hence a 2 here. Let's see if I'm balanced. This is 2 sodium, this is 1 sodium, so I need 2 on the left-hand side, right? Let's check off. One lead, good. 2 nitrate, excellent. 2 sodium, superb. 2 chlorine, excellent. Wonderful. Everybody agree with that? Balance?
Excuse me, sir.
Yes, go ahead, Felicia.
So for the last part with sodium, what was the chemical to the
All
back?
right, so it's sodium nitrate, so it is NaNO3. That's sodium nitrate. Remember, it's double decomposition in a cell. So what you're doing, you're interchanging the ions. So this is lead nitrate and this is sodium chloride. So this is would be lead chloride and sodium nitrate. All you're doing, interchanging the ions. All right?
Yes, sir.
All right, good work. All right, so we balance the equation. Next thing that we're gonna do is to split up the equation, split up each compound, right? Where applicable into ions. This is aqueous, so of course we can split it. So this is gonna give me lead Pb2 plus. So I'm now splitting, showing the charges. So this is Pb2 plus aqueous, right? This is 2 nitrate, 2 NO3 minus aqueous. So what I'm doing, I'm basically writing out the individual ions that now make up the molecule or the compound, right? And also telling the entities, the number of entities of each. So in this is 1 lead, 2 nitrate. So Pb2 plus, showing the charge of the ion. Nitrate is NO3 minus, is 2 nitrate, and it's 2 NO3 minus. Plus, follow me, sodium chloride, 2 Na plus, aqueous. It's 2 Cl as well, so 2 Cl minus aqueous. And this is gonna produce PbCl2. Do I split the lead chloride? Do I split the lead chloride? Let me see if we're learning. Would I split it? It is solid. Would I split it?
No, sir.
Excellent. So you keep it as it is. So you don't split solid. So it's lead chloride, solid state, plus this is aqueous, so we're gonna split this. 2 Na plus aqueous, right? 2 NO3 aqueous. Wonderful. The next thing that we need to do now is to get rid of our spectator ions. So like persons in the class now, that's just here and not following and not participating, we call them spectators. All right, good. So as you can see now, the nitrate here is aqueous. It's also aqueous here. So we remove it. What else can we remove? The sodium, right? Sodium is aqueous here, also aqueous here. So remove it. Spectator. We have any more? That's it. Everybody agree with me? Follow it. All right. Good.
Yes, sir.
Good work. Excellent. So of course, this is now gonna give us lead Pb2 plus aqueous plus the Cl that remains, 2 Cl minus aqueous, right? And that give us PbCl2 solid. And that's how you do ionic equations. Quite simple. Is it that hard? Chemistry is so beautiful. Wonderful. We're gonna work one more and then we're gonna move on to periodic table. So we finished about 3 topics just a while ago, if you don't realize. Give me a second. Everybody good so far? Enjoying the session? We're learning?
Yes, sir.
Yes, sir.
All right, good, good. The newcomers, not my students. My students are masters of these things. All the newcomers are good? All right, good. I want to ensure not going too fast, right? All right, I try to tone it down a bit. Give me a second. All right, let's go. So one more example and then we're moving on. All right, because remember, these students give us a lot of things to cover. All right, so we're looking on the reaction. We're writing the equation, Ionic equation for the reaction with magnesium and hydrochloric acid. Let's go. All right. So you guys gonna guide you through this one. So it's magnesium reacting with HCl. That's gonna produce magnesium chloride, MgCl2, plus hydrogen gas. All right, balance the equation for me. What goes where? Talk to me. All right. Colecia.
Place 2 in front of the hydrochloric acid.
So 2 in front of what? The hydrogen gas or the HCl? Which one?
The HCl.
The HCl. Excellent. So let's see if she's correct. So 2 in front of the HCl, that is 2 hydrogen on the left, 2 hydrogen on the right, 2 Cl on the left, 2 Cl on the right, and 1 magnesium on the left, 1 magnesium on the right. Excellent. She is absolutely correct. Let's go ahead now and try to break up the substance. So the magnesium remains as it is, right? You don't put a charge. So a lot of times students might put a charge. You don't put it because remember it's not aqueous. So it's not gonna have a charge. You don't split it up. So the charge is gonna be 0, right? Split up the HCl. So this is 2H plus, charge and hydrogen plus, right? Aqueous, excellent. 2Cl minus, right? So the 2 here is showing us that it is 2 hydrogen and 2 chlorine, all right? And we'll call this coefficient or stoichiometry. All right, good work. Magnesium here, so this is Mg2 plus. Now you can split it because it is now in a compound, right? Mg2 plus aqueous, 2Cl minus aqueous, good, right? Plus H2 gas, excellent. Sorry. Let's now get rid of our spectator ions. So we'll get rid of chlorine, aqueous, chlorine here, right? And then we're just writing back everything that left behind, right? Good. So this will be magnesium solid reacting with 2H plus aqueous, and that gives us Mg2 plus aqueous plus H2 gas. Good. Everybody understand that? Sorry. All right. So that brings us to understanding chemical formula, understanding atomic structure, understanding balance equation, and understanding Ionic equation. That's basically 3 topics wrapped up in one. Next topic, periodic table. Comfortable? Then move on, right? Periodic table and periodicity. Okay, move on. All right, good. Now, the periodic table is a listing of known elements ordered in terms of an increase in atomic number, right? Before Dmitry Mendeleev came about, well, Dmitry Mendeleev wanted it to be ordered in terms of mass number. But then there was this man by the name of Henry Moseley who came and said, no, man, we cannot do that because you're going to have some compounds, or some atoms rather, that have the same mass, and then it's going to cause confusion and all of that. So we say, all right, you know what? We're gonna order them in terms of an increase in atomic number. Now the periodic table is made up of rows and columns, right? In which the rows we call them periods and the columns we call them groups, right? Now at this level, why do we study the periodic table? And we're applying it to the CSEC chemistry syllabus and to pass papers. Now what they ask us is about strengths. So from time to time, you see they give us a periodic table and they put an element, for example, X, and they ask us and say, all right, how would X react with so on, so on? How would X react, right? And that is based on the position in which X is in the periodic table, which we're gonna discuss. Now, once you're talking about the periodic table, there are certain characteristics and parameters that we have to study. Let's talk about them. One, we have to know what is atomic radius, right? Good. We have to know what is known as ionization energy. Good. We have to know about shielding effect and nuclear charge, right? Nuclear charge. I'm gonna put NC for nuclear charge. You soon get used to me if you enroll with me. NC, I write a lot in abbreviations now. I don't like writing. All right. So NC, nuclear charge, and then we have electron affinity. Electron affinity or electronegativity. Now, all of these parameters is gonna help us in explaining what really takes place in the periodic table. Why is it that this species is more reactive than the next, and so on and so forth, right? Let us go. We're all ready? Ready to rumble? All right, good work. Excellent work. I love this batch of students. You guys are calm. You guys seem wonderful. I love that. Good. All right, so let's talk about groups. So we have 8 groups, right? And groups, as we say, going down, right? Now, the valence electron, right, tells us the group in which a given
Excuse me,
atom
sir.
is in, right? So, for example, yes, Fanisa,
Your whiteboard is like shining a bit, and I really can't see on the board.
Go again?
Your whiteboard is like shining a bit, and I really can't see on the board. Sorry.
Whiteboard not showing. All right, let me try to see. Showing up?
It's showing, yeah, it's showing, but not like clearly. Okay, I can see now. Thank you.
All right, good, good, good. Excellent. All right, so yes, so as I was saying now, right, the groups, the valence electron tells you the group that the atom is in. So for example, sodium here, whose electronic configuration is 281, it's saying to us that, okay, this is actually in group 1, right? Let's talk about trends in groups. Well, what is known as atomic radius. Now, the atomic radius, guys, is really the distance from the nucleus to the outer shell. So if we're supposed to draw an atom, right? Use my red marker. If we're supposed to draw an atom, what we're simply saying is that it's the distance from the nucleus to whatever outer shell that we have. So if this is the outer shell, this is the atomic radius. At this level, you don't need to know much about it. We're not going to go in depth. Normally measured in angstrom units, right? So that's the use of measurement for it. Now, why is this important? It is important because the distance based on the atomic radius, it can contribute so much to a lot of things. Let's look. Now, as you go down the group, what is taking place as you go down the group? As you go down the group, the number of shells is increasing. So, for example, sodium would be 281, then potassium would be 2881. So the number of shells is increasing. So because the number of shells now, guys, is increasing, it means then that the atomic radius is increasing as you go down the group. But what does this mean with regards to ionization energy, shielding, right, and the nuclear charge? Let's talk about that because that is what we're trying to discuss here. So as you go down the group, the atomic radius increases, right? So because the atomic radius increases, remember now that the nucleus consists of the protons and neutrons, right? The protons are positively charged and the neutron is neutral. It has a 0 charge. So therefore, the charge on the nucleus is positive. Now remember that on the shells, we actually have the electrons which are negatively charged entities, right? It therefore means then that there's an electrostatic, sorry about the noise. It therefore means then that there's an electrostatic force of attraction between the positive nucleus and the outer shell all the time, right? Which we call a nuclear charge. So now this nuclear charge, guys, is actually influenced by the distance moved. Let us talk about it some more. Let us look on sodium versus potassium. Follow me carefully. I'm taking my time. Open and breathe. So sodium actually have 3 shells, 2, 8, 1. Right? Let's call this shell 1, this shell 2, and this shell 3. And this is the atomic radius. Let us say that the atomic radius here is about 2 millimeter. 2 millimeter. Just using an hypothetical value for explanation. Potassium now has 4 shells. Right? Good. Right? 1, 2, 3, 4. Right? And this one, atomic radius is now larger, 4 millimeters. Let's talk about it. What is this saying to us? All right? Let's look carefully. The distance from the nucleus to the outer shell in potassium is greater than the distance from the nucleus to the outer shell in sodium. Makes perfect sense. But what else you realize taking place? In potassium, right, the number of inner electron shells is more than the number of inner electron shells in sodium, right? Notice this is 3 inner electron shells and this is 2 inner electron shells. So as you go down the group, because the number of shells is increasing, right? The number of inner electron shells is also increasing. But what does this mean? Remember, I just said that there's an electrostatic force of attraction between the positive nucleus and the electrons on each orbital. It makes perfect sense. That's the only way that you can have that, actually have that planetary model in which the electrons keep rotating, right? So it's that electrostatic force of attraction that is now holding the electrons around the nucleus. But as the number of inner electron shells increases, right? Remember that these shells will also have what? Electrons. So it's still gonna have an attraction. These will have an attraction to the nucleus just the same. It therefore means then that with an increase in inner electron shells, right? That increases what we call a shielding effect. So the outer electron here is now shielded from the full charge of the nucleus. Because it's now shielded from the full charge of the nucleus, right? The nucleus no longer holds it very strongly. So the outer electron, as you go down a group, is weakly held. So it is easier to remove electrons going down the group than to remove electrons that are higher up the group. Why? Because there is an increase in shielding effect brought about as a result of an increase in atomic radius. Everybody following me? Everybody following? So far, so good?
Also, yes, sir.
All right, good. Let's see how this is applicable now to ionization energy and electron affinity. What is ionization energy? Ionization energy at this level represents the minimum amount of energy that is required to remove electrons from the outer shell. So as you go down the group, the ionization energy decreases, meaning then that it doesn't take a lot of energy to remove electrons going down the group. Why? Because electrons going down the group are weakly held due to an increase in shielding. So as you go down the group, you realize that ionization energy decreases. Now, there's a question that came on a past paper question, and a past paper paper. A past paper, sorry, right? They ask, what is the trend with the ease of ionization? This word is key, ease of ionization. Now, while ionization energy decreases going down the group, the ease of ionization increases. Why it increases? This is saying to me, right? Ease of ionization is basically saying the ability to form ions increases going down the group. That is what it's saying, right? So don't get it twisted. Remember that ionization, right, refers to the ability to ionize, to form ions. So when they say now that the ease of ionization energy, the ease of ionization increases going down the group, it's simply saying to us that, guess what? It is easier to form ions going down the group, and it makes perfect sense because why? As you go down the group, it is easier to remove these electrons from the outer shells. So that is why ease of ionization increases going down the group. Everybody following me? We won't get it twisted enough. So ionization energy decreases going down the group because ionization energy, the amount of energy needed to remove electrons from the outer shell. But the ease of ionization increases, meaning that it is easier to form ions going down a group. We're all good? We're all good, right? All right, excellent. And of course, all right, so that is it for groups. Now, the syllabus wants us to look on groups 2, group 7, and period 3. So let's take a look at group 2. Group 2 is often termed as your alkaline earth metals. And it consists of beryllium, magnesium, calcium, strontium, barium, beryllium, magnesium, right? Calcium, strontium, barium. All right, that is what 2, 8, 18, 8, 2. 8, 18, 8, 2. Barium is 2, 8, 18, 18, 8, 2. All right. Let's take a look at this one. So looking on trend in group 2. So first trend is, of course, that the atomic radius is going to increase going down the group. Right? You will also realize that all elements in group 2, right, contains 2 electrons in their valence shell. All right. So the number of electrons in your valence shell tells you the group, while the number of shells tells you the period. So from time to time, once Csec brings a question that is pertaining to shells, for example, like this, all right, given that the magnesium electronic configuration is 282, what period it belongs to? It will be period 3, because this is 3 different shells. 1, 2, 3. All right. Good. All right. So all elements are in group have 2 electrons in their outer shell. Atomic radius increases going down the group. Next one is that the ionization energy decreases going down the group. So ionization energy decreases going down the group. You can add that. Another thing is that all elements here are metals. All elements here are metals.
Sir, your screen is no longer showing.
Go again, Rena?
Your screen is no longer showing.
Oh, well, I'm just dictating. I'm not necessarily writing, so you can just listen. Showing all right? Should be.
Yes, sir.
All right,
So-
good. All right, so all elements here are metals. All right, let me ask a question here. Let me see who's learning. So I've just said that it's easier to form ions going down the group. Would you expect then for metals, right? And in this example, like group 2 here, would you expect then that the reactivity will increase going down the group or it will decrease, and why? If ionization energy decreases going down the group and it is easier to form ions going down the group, would you say then that reactivity increases or decreases going down the group?
Sir, ionization increases.
No, I didn't say, I didn't talk about ionization energy. I'm asking a question. Listen to the question carefully again. Remember, chemistry is about not just about regurgitation, it's more so about application of the knowledge that you guys know. So I just said to you that ionization energy decreases going down the group. And I mentioned that it is easier to form ions going down a group, right? Because ionization energy is decreasing. So the electron in the outer shell is loosely held, so it's easy to remove. So now I'm asking you, with that knowledge, would you expect then for reactivity to increase or to decrease going down a group?
Sir, I would say decrease. I don't have a reason.
Increase.
Increase. There's no way it can increase. It have to increase. Remember, you know, what this is saying, that's why I said ease of ionization energy. Because it's so easy to form ions, it's going to be way more reactive. Right? Must be way more reactive because remember, guys, it's the presence of ions that cause a reaction. If you want to form sodium chloride, right? To form sodium chloride ionic lattice, it's really the electrostatic force of attraction between the sodium cation and the chloride anion that's going to cause the formation of sodium chloride. So it's the same thing here, right? The easier it is to form ions, the more reactive that species is going to be. So as you go down the group, right, there's an increase in reactivity. That is magnesium. So we're going to look on water, for example, the reaction with water. So magnesium will react with cold water. And this is an example that they always give us on give students most times, oftentimes on the exam paper, right? So magnesium will react with cold water, only with cold water, while the calcium will react rapidly with the same cold water, while barium and strontium will react dangerously, right, or violently with cold water, or with water overall. All right, good. All right, another trend. The compounds formed here, right, will conduct electricity. So they form ionic compounds. Of course, they are metals, so when they react with non-metals, they form ionic compounds, which can conduct electricity when molten or dissolved. Right, that's one more trend. Another trend is that the oxides and the hydroxides are basic. So all metals, hydroxides of metals and are normally basic, while the hydroxide of non-metals are normally acidic. When we start doing acid and base, if we do it tonight, then you'll see about that. Right? Next trend, the solubility of the oxides and the hydroxide increases going down the group, while all other salts, though, decreases going down the group. But for group 2, the solubility increases going down the group. And that that is based on the fact that because it is easier to form the ions, right? It is also easy to actually cause a separation to occur, right? So they are soluble. The solubility increases going down the group. So that is it for trend with group 2. Next one, we're going to look on the trend in group 7. All right, so group 7 will consist of fluorine, chlorine, bromine, iodine. That's fluorine, chlorine, bromine, iodine. First trend, which is quite obvious, all elements have 7 electrons in their valence shell. All right. All elements of an oxidation number of -1 Why minus 1? Because it has 7 electrons in the valence shell, so it just need 1 more electrons to get full octet. All right? So to gain an electron. So all elements have 7 electrons in your valence shell. And common oxidation state is -1, charge 1 minus. All right, good. We're still accepting persons to join the session. So if your friend needs the session, you can always send them. All right, good. The atomic radius increases going down the group as well. All right, let's go. All right, the melting point is gonna be increase going down the group as well. So once you look at non-metals, now one of the major things that influence the bonding is van der Waals forces. Now, van der Waals force, I'm not gonna get into it now, but van der Waals force is what we call an instantaneous dipole being developed. And it's also dependent on how large a molecule is. So as the molecules get larger going down, there's an increase in van der Waals forces that causes an increase in melting point. All right. So the melting point actually increases going down the group. Another thing to note is that the physical state of the elements will change, right? Good, Ivanka, right? So the physical state of the elements will also change from gas to solids, right? As you go down. And that is because of van der Waals forces increasing as you go down. So fluorine is a gas, chlorine exists as a gas, bromine as a liquid, iodine as a solid, astatine exists as a solid. All right, good. I'm going to ask a question to see if you guys are learning and if you can apply yourself. Because that's what chemistry is about. If going down the group, listen carefully. All right, let me not even start here. If electronegativity is the ability for atoms to gain electrons, right? To pull electrons to itself. And I would have said to you guys before that as you go down a group, the nuclear charge decreases. So it doesn't have that pulling effect anymore. Would you expect then for electronegativity for groups of the elements to decrease or increase going down the group?
Decrease.
What's that, Chris? What's that, Christine? Decrease. Everybody agree? Decrease. Makes sense? Excellent. Because remember that since that electronegativity is the ability to pull electrons towards itself, and the nuclear charge is decreasing, then obviously, right, it have to decrease. So it decreases going down the group, but it increases going up. So electrons, so atoms like fluorine is more electronegative than chlorine, which is more electronegative than bromine, which is more electronegative than iodine. All right, excellent. So we finish with group 7. We're now to period 3. So period 3, we're looking at sodium to chlorine, right? So we have sodium. Let's write it up. So we have sodium, right? 281, magnesium 282, aluminum 283, silicon 284, phosphorus 285, sulfur 286, of chlorine 287. What do you realize occurring as you go across period 3? Talk to me. What is taking place as you go across? What do you realize?
It's increasing.
All right. So first of all, the number of shells remains the same, right? That's 1. But as you go across, the number of valence electron increases by 1. Now, the mere fact that the number of valence electron increases by 1, therefore means then that the electron cloud on the last shell, or the electron density on the last shell, is increasing each time. But what does this mean for atomic radius and for nuclear charge? Because the electron density on your outer shell is increasing each time, right? Not necessarily the number of atoms, well, not necessarily that the number of shells is changing, but in this case is a case where the number of electrons in the valence shell is increasing. So what takes place is that the atomic radius decreases. Why it decreases? It decreases because the nucleus now, with an increase in the number of electrons on the outer shell, will have a greater electrostatic force of attraction to pull electrons to itself. Think about it. The nucleus being the north pole of a magnet and the electrons here being the south pole. If I'm supposed to add more south pole electrons each time, then the magnetic force is going to be greater, right? Which means then that the two magnets is going to pull at a faster rate as I increase the number of magnets, correct? Make sense?
Yes,
Makes
sir.
sense. It's the same thing that is occurring here. As we go across the period, the number of valence electrons is increasing. Realize 1, 2, 3, 4, 5, 6, 7. It's increasing. So because the number of valence electron is increasing, guys, right? The electron charge cloud or the electron cloud in the outer shell increases, which means then that the electrostatic force of attraction between the nucleus and the outer shell increases, causing then a greater pull. So the nuclear charge increases, causing a greater pull inwards, and ultimately decreases the atomic radius. So the distance gets a little bit smaller, right? So what does this mean with regards to ionization energy? Is once you go across the period, right, there's going to be an increase in ionization energy. Why? Because the nuclear charge increases. So the overall pull on the nucleus to the outer shell increases even more. So it's going to be harder to remove electrons as you go across the period. So ionization energy increases going across the period. Everybody follow it? Meaning it's going to take way more energy to remove electrons. Good to go.
Yes, sir.
But what does this mean with electronegativity? Electronegativity is going to increase across the period. And it makes perfect sense in both ways. One, as you go across the period, you're moving from metals to non-metals. Non-metals are very electronegative, meaning that they will pull electrons to itself. But not only that, because the nuclear charge is increasing, you have a greater affinity towards electrons. So it's pulling electrons even more. So that is why electronegativity increases going across the period. Excellent. That is it for periodic table. Pretty much in a nutshell. Everybody good with me so far? Yeah, I just said that. That it changes from metals to non-metals. So that is periodic table and trends. So that is about 5 topics down already. In a short space of time. Where else you'll get things like this? Where else? What we're moving on to now? Acid and base and salts. Acid base. Oh, people find acid base and salt difficult. I don't understand you guys. I don't understand you guys, man. Who you find acid base and salt difficult? Too simple. All right, so we're going to acid base and salt next. Take a sip of water. All right, ease back. Stretch your legs. And let's rumble. Everybody good so far with the session, enjoying it. We're learning, because that's the overall sense of being here. We're all learning. What time is it in Trinidad?
30 minutes past 8.
Okay, we have any Guyanese here? Just Trinidad and Jamaica?
No, sir, I used to.
Oh, what's that? St. Vincent? Oh.
St. Vincent is here too.
Oh. All right, so we're gonna go to acid, base, and salt next. Give me a minute. All right. So let's go now. So acid and base. Where's everybody? Still there?
Yes, sir.
All right, good.
Yes, sir.
So we're looking at acids and base now, right? I really don't know if people struggle with this topic or have issues with the topic, but let's go. Now, acids and base, right? What I want to know is one, what's an acid? What's a base? Reactions of acid, reactions of base. So acid can be defined in different ways at this level. We're gonna use the term that acids are proton donors, right? So acids are proton donors and bases are proton acceptors. Now we can have strong acids and we can have weak acids. So for example, if we're supposed to have something like hydrochloric acid, if we have a substance like hydrochloric acid is a strong acid. Why? Because it will dissociate completely when placed in water. So if you're supposed to place this in water, right, then it's gonna form hydrogen ions, H plus ions, and it's gonna form corresponding Cl minus ions. All right. You also have weak acids that are now incomplete dissociation. So incomplete dissociation, meaning then that if you have something like CH3COO, CH3COOH, which is ethanoic acid, right? And it's supposed to go in water, then you gonna get what is known as an equilibrium, right? When you reach at the K level, we'll dissect this some more. So this is gonna form an ethanoic ion. But remember that an acid is a proton donor. So what you realize happening each time, hydrogen is removing, right? Hydrogen is removing, right? So it removes and forms what is known as a conjugate base. You don't need to know about conjugate base pair as yet at this level. So it forms this species we saw, right? And H2 plus ions, right? That's pretty much it for acids. Now let's talk about general properties of acids. Acids are normally sour, right? It's why when you eat lime, I don't think anybody eat lime, but if it tastes lime, right? It actually have that sour taste, like even with oranges, etc. Because remember that they have loads of citric acid, right? They are colorless liquids. They are normally corrosive as well. We have different categories. What's this? All right. Oh. Rates of reaction and chemical equilibrium, Le Chatelet's principle. Our session, no, so I won't be able to actually do that. No. Yeah, I won't be able to do that. No. I'm not sure if I'm actually gonna be able to do that tonight, because I actually have some stuff to sort out as well regarding to a reaction that I actually have set up at work for some time. So I'm not sure. But I'll take a look when I get the chance to. All right, good. All right, so as I was saying, guys, sorry about that. All right, as I was saying, you have two different types of acids. You have organic acids, right? And you also have inorganic acids. So organic acids are those that people say they are God-made. So they occur naturally. So they occur in plants and animals. So for example, formic acid. You all know what's formic acid, right? Everybody know? It's the same thing as metanoic acid. It's the acid that is found in ants. That's why they always say that ants don't bite. Remember, ants don't bite or ants those things. Really, when they urinate or they pass the acid, right? So they pass that liquid on you, and because the pH of the acid is not correlating with the pH of your skin, that's why you actually feel that burn. All right. And of course, you have inorganic acids that are man-made. So you're looking at HCl, nitric acid, sulfuric acid, you name it. All right. Now, we mentioned before the strengths of acid. What's a strong acid? One that is completely disassociated in water. And then we said that weak acids are partially disassociated. Now, when you're talking about acid, one of the major things that you want to look on as well is talking about basicity. Basicity, also known as protonicity. All right, so basicity. Basicity, or protosity. All right, so basicity or protosity refers to now the number of hydrogen ions that will be liberated per mole of acid used. So if you're looking at something like HCl or even ethanoic acid, HCl or ethanoic acid, these are all known as monobasic species. Why? Because when they are disassociated, it's gonna not just liberate one mole of hydrogen ions. Now, you have what are known as dibasic acid, like sulfuric acid. These are acids that will now liberate 2 moles of hydrogen ions because they have 2 hydrogens. So like H2SO4 would liberate 2 H plus ions. So we call it a dibasic. And then of course we have a tribasic, which would be like phosphoric acid. All right, so we're good to go from there. Now we're gonna look on the reactions of acid, right, that they undergo. Give me a minute. All right, so no problem. So I'll give the book a review, just to make sure that the formulas are correct, and then we should be good from there. All right, so guys, I'm dropping a book on mole concepts. I wrote a book on mole concept, very good book, right? You can access it. If you're in Jamaica, you can access it on the website. You can buy it. It's gonna be in bookstore. You can call me. You can message me. Can get it. Or if you are not in Jamaica, you can purchase it on our website. Right? So very, very good mole concept book. It dissects mole concept from 0 to 100. All right, good. All right, so let's look on reactions of acids. So looking at first acid and base. Acids react with base to form salt and water. All right, we're going to give an example. So if we have sodium hydroxide react with HCl, that's going to form sodium chloride and water, right? We also have acid and metals. So if we have acid and metals, that's going to form salt and hydrogen gas. So for example, if I have sodium react with HCl, that's going to give me sodium chloride and hydrogen gas. I can also have acid react with carbonates, which going to give me what? Salt, carbon dioxide, and water. That's salt, carbon dioxide, and water. So if I have sodium carbonate Na2CO3 react with HCl, I'm going to get sodium chloride NaCl plus H2O plus CO2, right? And I can also have acid react with hydrogen carbonates, just the same. I'm also going to have a marathon on Sunday, a paid marathon on Sunday, right? It's going to be a whole day marathon for 3,000 Jamaican dollars. Very cheap. It's going to be from 10 to 5 o'clock. If you're interested, you can sign up. I'm just giving you guys the opportunity, you know, to learn and go and giving back for this Easter, right? So it's HCl react with sodium hydrogen carbonate, that is NaHCO3. And that's going to form sodium chloride NaCl plus H2O plus CO2. All right, so that's pretty much the reactions of acids. All right, excellent. Now, see that we've been talking about salts. Let's just, all right, after signing up, after class, we can talk about signing up for a program, right? It's a very good program. I don't even need to try to sell myself. I'm not trying to do that. But you guys would have been here and see what we have been doing and what we were capable of achieving in short space of time. So just think about where you can go in the next month. You know, it's just ridiculous. But anyways, let's just finish this, then we'll talk about that. So salts, as you can see, guys, salts, these are substances, right, that are formed when the hydrogen of an acid is replaced by a metal. So that's how you define salt. It's a common past paper question definition. So a salt is a substance that's formed when the hydrogen ion of an acid is replaced by a metal ion. All right. All right, good. All right, so let's now look on, and everybody by now is supposed to know how to name that. Let's now look on bases. So bases are the opposite of acids, right? So they are substances, they are proton acceptors. Or you can say that they are substances that will react with H plus ions to produce salt and water. All right? But bases now, properties, they are normally bitter. So one, they are normally bitter. They are normally corrosive. And they are normally soapy. You can add that as well. Reactions of base, they react with acid to form salt and water. They will also react with ammonium compounds to form salt, water, and ammonia. So for example, if I have sodium hydroxide, let me show you. So if I have sodium hydroxide reacting with ammonium chloride, NH4Cl, that's going to form NaCl, H2O, and NH3. All right, so it reacts with ammonium compounds rather, to form salt, water, and ammonia. All right, good. Now, since that we're an acid and base, one of the major things to talk about is titration. So let's just run through titration quickly and talk about neutralization point. So titration involves a volumetric analysis of a titrant, guys, and a titrant. A titrant is the substance that is normally in your burette, while the titrant is a substance being analyzed for that's normally in your conical flask, right? Now, the purpose of it and what you're actually trying to do, what is going on here? Purpose of it and what you're... Huh? Okay. Cool. All right, cool. Yeah, so the purpose of it and what you're trying to do is essentially, well, you have different type of titration, but one that we focus on is volumetric using indicator, right? You also have thermometric. I think there's a past paper question. Sometimes they was asked on thermometric in which they use styrofoam cup. And there is the common past paper question on thermometric is one in which you'll be given a graph. Not sure if when you practice you ever see that one, in which they ask you what is the highest point reach on the graph. So this is normally the graph in which you're adding the base or the acid and you're watching how the temperature rises. Now this point is known as your neutralization point, which also represents your equivalence volume, right? And of course, we know that the neutralization point is the point at which all acids and bases are completely reactive, right, to form water. All right, good. Now let's look on neutral substances. So we're on acid and base, looking at neutral substances. We're going to talk about acid anhydrides, acidic oxides, you know, amphoteric oxides and all of that. So neutral substances are substances with pH of 7. We can have acidic oxides, which are normally formed when non-metal oxides, well, acidic oxides are non-metal oxides, but when they react with water, right, they will form acids. So oxides of most non-metal are acidic oxides. So looking on acidic oxides, right? And sometimes they are referred to as acid anhydrides, right? So if I have SO2 reacting with water to form H2SO3, which is sulfurous acid, then the SO2 there, because it's a non-metal it's the oxide of a non-metal, it's an acidic oxide. Same thing if carbon dioxide react with water, it's gonna form carbonic acid. Neutral oxides now are oxides that are neither non-metal nor basic. So that would be like carbon monoxide, nitrous oxide, and dinitrogen oxygen. So neutral substances or neutral oxides would be carbon monoxide, NO and N2O, right? And then we have our basic oxides, which are metal oxides. So oxides of non-metal, oxides of metal are basic oxides. So if I have something like magnesium oxide, then this be a basic oxide because it's an oxide of the metal. All right, good to go. And then we have what is known as amphoteric oxides. And these are oxides that will now react with both acids and base. All right, amphoteric. As the name suggests, ampho means both or ambi. Right, you're looking at things like zinc oxide, aluminum oxide, or lead oxide. All right, and these will react with both acids and base. Now, if it react with an acid, so if you have something like lead oxide react with, the lead oxide react with HNO3, that's gonna form lead nitrate. Right, and water, right? But if you have lead oxide now react with sodium hydroxide, right, it's gonna form like a plumbate. Gonna form lead, sodium, so that's NaPbO2, which is sodium plumbate, water. Right, so these are the reactions of different acid-base properties. So you have acidic oxides, which are non-metal oxide, basic oxide, which are metal oxides, and all of that. So that is pretty much it for acid and base. I think where the problem lies with acid and base is regarding to salt and salt preparation, which we're now gonna look on. All right, so we're now looking on salt. So finish with acid and base, and we're now on salts. Chemistry look easy now, eh? Talk true. That one is the same subject, not true.
So you're making it look a little easy.
What's that, Felicia?
You're making it look a little easy now.
It's not that hard, man. It's simple, man.
So when are we having our next session?
Well, again, I didn't hear that.
Are we having another chemistry session like this, or this is the only
Yes,
one?
man. All right. So every Sunday, my students here, we have chemistry sessions on Sundays. We have some stalwarts like Jada Johnson, Jada Ogle, Kishana, Brianna, Rihanna, Brittany, all of them, these students are here. So they are in my program. And also that I miss, I think is here as well. I'm not sure if everybody's here. But yeah, we have session every Thursday. 6. What time is it, Jada, on Thursdays? I don't know. What, 5:30? What time is class again?
Sir, it's always been like 6:30, or you don't make it.
Oh, it's
6:30.
Eddie. Yeah, I'm Eddie. All right.
You make it to 7 o'clock.
So yeah, so 6:37, and we finish at what time? We don't have a time that we finish.
Sir, you don't have a time.
We don't have a time, right? So if it's free, if we feel like going to 12 o'clock, we'll go to 12. If we feel like going to 1 o'clock, we go to 1. Because at the end of the day, it's all about the student successfully, right? Just the same, if on Sundays we vibe. So if it's 5, we start at 5:36 and we just go on till they feel tired. If they feel tired at 10 o'clock, then I might feel lenient and say, go to your bed, Jada. It's time for you to get some popcorn and watch a nice movie, Jada. and go to your bed. Or I can say, all right, we're gonna go to 1 o'clock or 3 o'clock. So you can tell mommy or daddy to put on some coffee for you so we can stay up. Yes, short stuff. So what happening? I see your hand up. What are you saying? You're talking to me?
Sir, question, what time you finishing tonight?
What time we finishing tonight? What time should we finish? I'm gonna hear what the math says. What time we finishing, guys? The maths.
9
o'clock.
9 o'clock? Not you, Kishan. I want that student that is not enrolled with me. What time we want us to finish? 8:30? Brianna Edwards? Why
I don't
8:30?
mind the time, sir.
8:30? Is this, wait, question. Is this the same Brianna Edwards in our session? In HTS? That's enrolled with our other subjects, Brianna? Is it Brianna? In which sub? That's IT and bio. Is it IT and bio or pure B, pure A? I'm not sure. I don't know. Really? So all this time you do chemistry? You're joking. You're joking, Brianna. What? Are you not here? You're joking, man. I have to talk to mommy. I definitely have to talk to mommy. So what time you guys say we finish? We have another chem class. Whoa. Oh my, I'm so sorry that you're not with us for chemistry. Oh my God. I wanna cry. What time should we finish, guys? 12 o'clock Jamaica time? What time you want? Talk to me.
Sir, it like near to 9 o'clock.
8 o'clock? Oh my, I thought you guys loving the chemistry. I want more sessions. You don't want me to complete the syllabus. What is going on?
Sir, I still finished the syllabus.
You guys not gonna get another session from me like this, you know. Unless you sign up for my program, then sure. But when I'm too busy to do sessions like these, and I'm gonna cater mostly for my students. So if you want, you can definitely enroll, but this is a free session, right? So I can go to 5 o'clock in the morning tomorrow if you want. But definitely I will. But anyways, though, yes, you guys say you wanted to finish 8 o'clock. Sorry, so let's see. You guys, I'm working with 8 o'clock. All right, cool. That's what you said. All right, so let's talk about salts,
Sir?
right? Yeah, quickly, make it quick.
After we do Redox.
After Redox, well, you can sign up for one of our sessions and we do Redox with you.
Sign up for one of your sessions. So.
You can sign up for one of my sessions. Let mommy call me. 202-6446. Let daddy call me. Talk to me, guys. Why are you doing that? I said Jamaicans don't love spend money. You know? Why? Education is an investment. You know that? Education is an investment, man. With the discount packages, right? And you're getting elite tutoring at the best. You're joking, man. All right, so salt. So we mentioned that salt is a substance, right? That is formed when the hydrogen ions from an acid is replaced by a metal. Now, when CSC brings salt question, they always ask us about two things. Sometimes. So you would see a lot of popular question. Telling this as a secret. We're telling this as a secret. Shh. So popular question that normally asked is define normal salts and acid salts. Very important. Normal versus acid salt. Now, a normal salt, right, is defined as a salt that contains no replaceable hydrogen ions and whose pH is 7 or neutral. So normal salts contains no replaceable hydrogen ions, while acid salt contains replaceable hydrogen ions and whose pH is below 7. So for example, they will give us a question and say, if sodium hydroxide reacts with sulfuric acid, write an equation to represent a normal salt forming and an acid salt forming. So the normal salt here will be sodium sulfate, Na2SO4, right? But the acid salt would be what? Obviously, one in which hydrogen is contained. So it's going to be sodium hydrogen sulfate, NaHSO4. All right? Simple as that. So normal salt don't have hydrogen. Acid salt have hydrogen. All right? Simple. We discussed solubility of salts already, right? In which we talk about sulfate, that. Talk about the decomposition of salts, in which carbon is decomposed to oxides and carbon dioxides, right? Nitrates decomposed to the oxide, nitrogen dioxide, and oxygen, and hydroxides. Hydroxide will decompose to oxides and water. So you can add that. Hydroxide ions or hydroxide salts will decompose to oxides and water. So for example, if I have something like copper hydroxide CuOH bracket 2, that's going to decompose to give me CuO plus H2O. All right? Quite simple. Chemistry is so simple, man. Oh my God. Here's the big boy now where I want a lot of you guys to pay attention. Salt preparation. Which method to use? So this is where the hiccup is with salt. All right, let's go. Remember, you still can invite your friend to come on to this free session. Still open. It's never too late. Right?
Can we have like a 5
It's never
break?
too late. Go again? What's that? Huh? Oh, yeah. Oh, I'm going. Somebody was asking when again I'm gonna have a session. I'm having a session on Sunday.
Right now, can we have like a 5-minute break?
What's that?
Can we have like a 5-minute break?
A 5-minute break?
Or even less?
You're tired? Oh, Shauna, you think they could manage our sessions?
I mean, not sure.
No, I'm not tired. I want to go pray, come back.
Yes, I think Felisa was saying something. My internet went. What's up?
I was asking for a 5-minute break.
No, not Fanisa, not Fanisa. Felice.
Says actually Felicia.
Yeah, what's up?
So I wanted to know when I finish if you're gonna do organic chemistry.
When I'm finished, as in when I'm finished tonight?
No, like it's a fix.
Oh yes, I'm gonna revise organic chemistry with my batch of students. If you want that to be done, or if you want that revision session, then you can enroll for that session. Sure. I'm not sure if we can do it tonight because we're gonna finish. It appears so if we finish 8 o'clock. So we'll just worry about it pop or it pop. That's what Jamaicans say. Rihanna, what's up?
So could we do Redox tonight?
Could you do what?
Redox.
Rihanna, first of all, you enroll in my sessions, Rihanna. You're gonna come Sunday. So if we don't do Redox, we're gonna do it Sunday. Don't.
So it's because you said you were doing section A, so the start.
Yeah, but sure, but your peers just said to me if you finish the class 8 o'clock, I know it's 7:48. So I'm not gonna do that. Think about that.
Sir, whatever you don't get to do now, you do it Sunday.
They just said to finish 8 o'clock. So now I asked the question, when should I finish? And they said 8 o'clock. You understand? You have to work with them. And either way, Rihanna, you don't need to worry. Remember, you're in my program. So if you don't get, remember we have a schedule, Rihanna. We follow protocols, Rihanna. You know what we're doing. So if we don't do it tonight for you, Rihanna, you're good to go. You don't have nothing to worry about, really. You don't know what you go already, man. Come on. No. You're good. You're good. Understand? If we don't do it, you're all right. But if we don't do it for the person who actually want it to be done, then they have to book a session with us to get it done. That's all. So if you're really interested, just enroll. No, killer. Honestly. Let your mother, let your father, whoever your guardian call me. Right? And it's cheap. See, it's cheap. We're literally giving you away, just giving away the sessions, literally. You came up, you guys come here and you see how we operate, literally. And this is just on a day that we just vibing. We didn't even going intense like that. Literally. It's an experience on our own. You get me? All right, so let's just finish up this though. If we can do Redox, we'll do Redox tonight. But if not, my students will get Redox done. But I don't think I'm going to have a session like this for now. Right? Oh, see it there. Kishana put it in the group. If you can't stay up until 12 or 1, don't bother come. Kishana, why you so harsh on the people them? Why you doing that? Oh my God, don't do that. Don't say don't bother come. But yes, the sessions are normally very long. The sessions are normally very long, I must say. I don't even time waste. That's one. If you're serious about learning, you enroll, but the sessions are normally very long. And they'll be very late in the night. Right? So it's a good advice. But it's up to you guys. We're not forcing anyone to come. I just love to help students. And I'm helping students out with care right now. So salt preparation. Let's jump into this because we have a limited amount of time anyways. Come like Rihanna have a friend in the class and the friend I said, make him go through salt. Read that one, please. You really? You can make your friend come in for the program, man. Yes. I want that discount packages there. Referral discounts. Right? Sessional discounts. Come on, man. All right. Salt preparation. So we have different methods in which we prepare salt. We have precipitation. Now, precipitation is where we want to prepare insoluble salts. And insoluble salts are formed when we react two soluble. Well, let me pause there. So, precipitation, that's one method of salt preparation. Now, precipitation is normally formed by reacting two soluble salts. Listen carefully. The precipitation is used to prepare insoluble salts from two soluble salt that contains ions of the insoluble salt. So let me go again. Precipitation is used to prepare insoluble salts by reacting two soluble salts that contains the ions of the insoluble salt. What do I mean by this? If I want to prepare lead chloride is insoluble. I would need to have a salt that contains lead in it, that is soluble, and I need to have a salt that contains chlorine in it, that is also soluble. So in this case, I would have lead nitrate, because all nitrates are soluble, reacting with a soluble chloride, that's sodium chloride. Now, if you react with sodium chloride, this is going to form lead chloride and sodium nitrate. So let me carry you guys into the lab now, because as I mentioned before, this is what I do on a daily basis, practical chemistry, right? So I'm not necessarily a teacher. Let me put that out there, my chemist by profession. All right, so I have lead nitrate reacting with sodium chloride forms lead chloride and sodium nitrate. So going in the lab now, we'll have some lead nitrate and we'll have some sodium chloride in some conical flask or beaker. Now, when we react the lead nitrate and the sodium chloride, what we're gonna see some deposition. some deposits right here at the bottom because it's the lead chloride. So the lead chloride is gonna sit at the bottom, right? While the nitrate, the sodium nitrate here sits at the top. So all we're gonna separate them. All we need to do is to one, we can decant, just pour it off, or we can filter. If we filter, it means then that we have the lead chloride remaining. Well, the lead chloride will be in the residue in the filter paper while this pass through. So all we need to do now, if it's in the filter paper, we can just take a wash bottle with some water, distilled water or deionized water, because we don't want to contaminate the salt. Wash it off, allow all of it, any spectator, right, ions or any foreign matter to go through, right, and then we air dry it or we can oven dry. So that's one precipitation to form insoluble salt. Then we have direct combination. So next one, we have direct combination. You know, if I was like you guys, and I'm having this session, may I tell the truth if we go to 1 o'clock? I don't understand you guys. So you guys say 8 o'clock?
Sir, I have so much stuff to do tomorrow to deal with like coming up.
You know that after this, I have a session with some students from UE. You know, literally. And we're going, what time? We're starting what time tonight? We're starting 10 o'clock, finishing 4:30 in the morning. All right, let's go. So direct combination. Now, direct combination, guys, right? It's used to prepare binary salts, which may react with water. So if you're looking on, it's basically two elements make up the salt that are heated together. So if you're looking on just two elements reacting, so if you have an iron and a chlorine, Fe plus chlorine, right, to form FeCl2. That's how your direct combination actually occurs, right? That's direct combination. Then we have neutralization. That's another form of forming salts now. So this is 3 we've gone already. And then I'm gonna show you guys the salt preparation. We call it the tree of salt. All right, somebody put my contact there, any one of my students, 202-6446. All right, looking at neutralization now. So this method is used to prepare soluble salts, right? Where an acid is neutralized using a solid method. So it's used to prepare soluble salts. So it can either react an acid and a metal. Neutralization, so it can react an acid and a metal. This is gonna give us salt and hydrogen, right? Can also react. So remember, neutralization used to prepare soluble salt, right? We can also have an acid and an insoluble oxide. Acid and an insoluble oxide reacting, and that's gonna form salt, right? And water. Then we're gonna have an acid and carbonate, and that's gonna form salt, water, and carbon dioxide. Gianna, is Gianna here?
I'm here.
Oh my God, how are you? How is everything going on so far?
I'm fine.
Good. This is one of my students, guys. Don't worry, I'm pretty close to them. All right, so I'll just pick up on them. All right. I think I saw Brianna. I'm not sure if I saw Azar and some others. All right. Lorian is here. Oh, that's fine. All right. Good, Gigi. All right. So acids and carbonate, and of course, acid can react with alkali to form salt and water. All right. Now, because the salt is actually soluble, then you realize that you need to actually crystallize, use crystallization, because it's going to be soluble. You can't decant or you can't filter, because what you're going to filter? You don't have any residue, right? So you actually need to crystallize it, right? Just like how salt will dissolve in water, so you pass it through crystallization. All right, so we look on neutralization, we look on direct combination, look on precipitation, right? All right, so I'm gonna give you the flow chart now of salt preparation. Let's go. All right, we might can do redox reaction tonight, by the way. All right, so I'll run through it with you guys, and that will be it for tonight. Next, so we can pick up, so my batch of students there, we can pick up from electrolysis and energetics and do a mole concept marathon, and then we move on to organic chem revision. So we were actually in revision. My set of students would have finished with the syllabus, and we're revising. All right, let's go. All right, so this is the flow chart or the flow diagram for salt preparation. All right, it's very important. So the first thing that you ask yourself is the salt soluble? Right? So once you get the salt, that's why we give it a solubility table. Is the salt soluble? If the salt is not soluble, or not, I'm frozen. All right, good. If the salt is not soluble, if it's a no, then we use precipitation, right? Ionic precipitation, all right, to prepare it. Now, if it is soluble, we then ask the question, is it a sodium? So if it is soluble, yes. Is it sodium, potassium, or ammonium salt? So ask if it is soluble, ask if it is sodium, potassium, or ammonium salt. If it is, then we have to prepare it by titration. That can involve rapid acids and base, acid and metal, whatever, right? If it is not a sodium, potassium, or ammonium salt, we then ask the question, is it anhydrous or a binary salt? So if it is, titration. If it is not, is it binary or anhydrous? Everybody know what's an anhydrous salt? What do I mean by anhydrous?
There is no water molecule present.
Excellent. So there's no water molecules present. Wonderful. All right, good. Internet, let me check on this. All right, so my camera is gone because my internet dropped. Give me about a minute to come back in quickly. All right. All right, let's go. Fittest of the fittest. I'm going to say we have 60 persons in the class. Right now, I'm so I go all out. All right. So ask, is the salt soluble? Right? If no, precipitation, yes. We'll ask the question, is it potassium, sodium, or ammonium? If it is yes, we use titration. If it's no, we'll ask if it's a binary or anhydrous salt. Anhydrous means that it don't have water crystallization. Now, if it is a binary salt, obviously we use direct combination, DC. But if it is, that is, if it is a binary salt or anhydrous, if it is not though, right, we use neutralization with insoluble metal base or carbon. So just neutralization reaction. All right, that's how we prepare. We're gonna apply our substrate now. Give me a minute. All right, good. All right, let's look on preparing. How would I prepare a magnesium sulfate salt? Let's look on that. So I'm going to use this method. Help me out with it. Firstly, is magnesium sulfate soluble? Just do the solubility table. Is magnesium sulfate soluble? No. All right. You say that it's not soluble. Sure. All sulfates are soluble except the lead sulfate and bare sulfate. Magnesium sulfate soluble. It is soluble. All right. Good. Next question. You ask yourself, is it a sodium, potassium, or ammonium salt? No. Is it a binary salt? It's not a binary salt, and it's not an anhydrous. Well, it is an anhydrous salt, but this is really for binary salt. I don't like to use. So yeah, but it's not a binary salt though, right? Because it's not made from two substances. As you can see, it's three different elements here. I soon come to, I think that's Gianna. Soon come to the right? So it's not a binary salt. So what we have to use is neutralization. So we can react something sulfuric acid with magnesium hydroxide, right? So it's an acid and a base reacting. So we're gonna get magnesium sulfate and water. Now what I have to do is to recrystallize the magnesium sulfate to get it. Yes, Jana?
So I was asking what's a binary salt.
Oh, so a binary salt, bi means two, right? So a binary salt is a salt that is made up of just two elements that doesn't require like a given reaction. It's normal like eating. So that's how I would say ferric chloride. That would be like a binary salt because it's just iron and chlorine in its natural state. Or either sodium chloride is a binary salt. Sodium and chlorine in its natural state. That's why you call it binary. All right.
Okay.
Yeah. So like magnesium chloride is also a binary salt. So it's any species that involves the elements in your natural state. All right. So that is it for acid, base, and salts. We're all comfortable. Feel like we're a bit more confident in acid, base, and salt. Ishana, you requested it. How you feel?
Good, sir.
Everybody? The outside students, we good?
Yes, sir.
All right. And we're on our final topic for tonight, which is redox reaction. Wow. Rihanna, you can stretch your legs, man. Redox reaction. Quite simple, quite easy. All right, let's go. Isn't chemistry easy, guys? Just look at it. It looks so hard after all, don't it? That's true. It looks so hard after all. Simple 1-3, man. Now, so it is easy. It's easy, man. It's just about applying yourself, man. Don't make it hard, man. All right, so looking at redox reaction. So redox reaction is where oxidation and reduction is taking place, right? At the same time. We're going to define both of these parameters, oxidation, and we're going to define reduction. Now, they can be defined in different ways. One, they can be defined in terms of oxidation number, right? They can be defined in terms of electron transfer. They can be defined in terms of oxygen. They can also be defined in terms of hydrogen. Now, a lot of times persons use the term oil and rig. That is when you're referring to like electron transfer, in which oxidation is loss and reduction is gain. Let's concentrate on oxidation. So oxidation can be defined in terms of, so we're going to define it in terms of each parameter here. Because as I said, these are the parameters from which you can define oxidation and reduction, each of which are the opposite of each other. So if you're defining oxidation now in terms of oxidizing number, then oxidation is defined as the increase in oxidation number, right? So it's an increase in oxidation number. Increase. With electron transfer, it is the loss of electrons. In terms of oxygen, it is the gain of oxygen. In terms of hydrogen, it is the loss of hydrogen. So from time to time, you'll see a lot of persons, or you'll see different scenarios, and they say, tell us whether oxidation or reduction have taken place. So what you have to do is to analyze the equation or analyze whatever that you're looking at and see whichever of these parameters that they are looking at. All right, which I'm going to show you guys soon. Now, reduction is the reverse. So reduction now. I can't believe that you guys almost finished my marker. Brand new marker, my boy. I can't believe, man. All right, so oxidation number. So in terms of reduction now, ON oxidation number, it will be a decrease in oxidation number. A decrease, right? In regards to electron transfer, it's going to be a gain in electron. In terms of oxygen, it's going to be a loss of oxygen, right? And in terms of hydrogen, it's going to be a gain in hydrogen. All right? Good. So let's look on some reactions. Please to grab that off quickly. All right, so we're going to look on hydrogen and oxygen and tell whether or not a substance is oxidized or reduced. All right, let's go. Everybody have this off? Have it off already? All right, good. Mhm. Chemistry is so beautiful. Let us say that we have this reaction involving the formation of hydrochloric acid. So it's hydrogen reacting with chlorine to form HCl. Let's look. From this then, we could say that chlorine is reduced. Why? If you realize chlorine would have picked up an hydrogen, that is, chlorine on the left-hand side was hydrogenless, meaning no hydrogen combined, but on the right-hand side, hydrogen combined. So chlorine gains hydrogen. So because chlorine gains hydrogen, and looking at the definitions that we have, we can say then that chlorine would have been reduced. Make sense? Make perfect sense, guys? Talk to me. Makes sense, right? Good. Come on, man. Everybody sleeping? Where's, well, 50 odd persons. Where's everyone? I'm not hearing from you. What to you? Wake up, man. You sleep when you're weak. You sleep when you die. Come on, man. Come on. Exam paper set already, you know. We have to be humble and we have to be hungry. Hungry for the grade 1. Hungry for the straight A profile. Right? Winners win. Let's go. So we're looking now on this reaction. Turn off the ring light. All right, let's see. It's better now. That's fine.
Yes, sir.
All right. So let's look on this now. So we have magnesium reacting with oxygen. You guys can see this green marker?
Sir, just use the blue one.
All right, use the blue one. Anything you want to send about it on some scale. So use the blue one. So magnesium reacting with oxygen. That's going to form magnesium oxide. What is this saying to us? Is it right for us to say then that magnesium is oxidized? Makes sense? Seeing that magnesium gains an oxygen? Makes sense, don't it?
Yes, sir.
Ah, Rihanna, where's Rihanna?
Yes, sir.
Remember that you need this session, you're saying. So we want the participation from you. It's key. Because you demand it. Come on, wake up. All right. Let's now look on lead oxide reacting with carbon. So lead oxide reacting with carbon, and it's forming lead and carbon dioxide and carbon monoxide. What can we see? Over thing freeze. What can we see here? It can therefore be said then that the lead, see that lead lost oxygen, right? It should have been it lost oxygen, so of course it would have been reduced, while the carbon is oxidized. Make sense? Look on the reaction. Look on the reaction, guys. So lead, this is lead oxide, right? Moves from lead oxide to lead. So can we say then that lead, since that it would have lost oxygen, is reduced, while the carbon gains oxygen, hence oxidized? Make sense? Excellent. Good work. All right. So we understand or we define then reduction and oxidation in terms of hydrogen and oxygen. Now we're going to look on oxidation number and calculating them and how we apply them and all of that. All right. All right. Let's go. Quite simple. Now, oxidation number, guys, refers to the number of electrons that is transferred or shared with an element forms a compound. It is normally the charge on the compound. The only difference is that the symbol comes first. So for example, magnesium, the charge on magnesium is Mg2 plus. So the charge is 2 plus, but the oxidation state is plus 2. So that is the difference, right? Now, a point to note is that metals tends to lose electrons, as was said before, right? So they're gonna have a positive oxidation state, while non-metals on the other hand gains electron, so they're gonna have a negative oxidation state. So for example, if I'm looking on something like iron, then iron here, right, will lose 2 electrons, right, to form Fe2 plus. With something like a chlorine would gain an electron to form a Cl minus, right? And we call these the half equation, right? So non-metals gain electrons, metals loses electrons, right? So metals, because they lose electrons, metals are oxidized, right? While non-metals, because they gain electron, they are reduced, right? Good to go. What the syllabus wants us to do is to understand how to calculate oxidation numbers. There are some rules that we use. Let us talk about them. Pay attention. Let's go. The first rule to understand is that oxidation state of uncombined element is 0. Meaning that if you have a species that is not reacting with any other species or it's not in a compound, its oxidation state is 0. So first rule, so calculating oxidation state, and the first rule is that oxidation state of uncombined species is 0. All right, you get that? Second, the oxidation state of monoatomic ions is the same thing as their charge or their valency. Remember, I don't really write, I dictate a lot, all right? So first one, as I said, oxidation state of uncombined species, meaning species in their natural form, not combined, right, is 0. Second, the oxidation state of monoatomic ions, meaning when the ions are formed, the oxidation state is the same as their charge. The oxidation state of hydrogen is +1, except when it is in an hydride. So the third rule, oxidation state of hydrogen is +1, except when it is in an hydride. And what do we mean by hydride? An hydride is a metal and an hydrogen reacting. So for example, if I have something like NaH, this is sodium hydride. So we're saying that when it is in an hydride, the oxidation state is -1. All right, good. Next rule, the oxidation state of oxygen is -2, except in peroxides and superoxides. Except when it is in peroxides and superoxides, where it is -1. So this is peroxide, all right? Where it is -1. Now, when we're looking on binary compounds, meaning that two substances in their natural state, the oxidation state of the more electronegative one would get the more, well, the more electronegative species will take the negative oxidation state. All right? So for example, if we had something like ammonia, NH3, the nitrogen will have the more negative oxidation state. All right, and then finally, the rule that we need to know is that the sum, right, of the oxidation state of neutral species or neutral compound is equal to 0. Sum of the oxidation state of neutral compounds is equal to 0. All right, so let's go. And in some instances, if you have a charge, right, the sum of the oxidation state is equal to the charge. So we're looking at 2 examples here. So they say, find the oxidation state of sulfur in copper sulfate. The first thing that you want to do is to equate the entire sum of the oxidation to to 0. Right? That is the oxidation of copper plus the oxidation of sulfur plus the oxidation of oxygen must be equal to 0. So we're going to basic school with maths now. The oxidation state of copper is what? Plus 2, right? Because that is the charge on the copper here, right? Remember, copper is divalent, it can be 2 plus or it can be plus. But this one is plus 2. So the oxidation state of copper is plus 2, plus the oxidation state of sulfur. We don't know that. That's what they want us to find. So we'll put that X. Plus the oxidation state of oxygen. What's the oxidation state of oxygen? The charge on oxygen is 2 minus, so the oxidation state is minus 2. But remember now that we need to also include the entities that is in it. This is 4 oxygen. So this would be minus 2 times 4. Hence, it will be plus 2, look carefully, plus X, plus minus 2 times 4 is minus 8. Minus 8 equals to 0. Simple mathematics, let's go. Plus 2 plus X minus 8, right? 2 minus 8 is minus 6, so that X minus 6 equals 0. We want X, so transpose carrying over the minus 6, X is equal to positive 6. Are we seeing that? Following me?
Yes, sir.
Following me? All right, let's try one more. Looking now at the oxidation state of chromium, right? So chromium, grab this off quickly, I'm moving now. All right, good. Looking now at the oxidation state of chromium in Cr04 2 minus. All right, let's look at it. Same vibe. Now, this, however, is not a neutral species because it's actually of a charge. So the sum of the oxidation state is going to be equal to minus 2. We want to find the oxidation state of chromium, so we're going to put an X, right? Plus the oxidation state of oxygen, which is minus 2. It's 4 oxygen and it's 4. So it is X minus 8, minus 2 times 4 minus 8, equals to minus 2. Transpose. X is equal to positive 8 minus 2, positive, carry over 8. 8 minus 2 is 6, X is equal to plus 6. We're all following? See? Looking simple, don't? Easy breezy, squeeze the lemon, squeeze it. It's not as hard as you think. Chemistry is too easy for you guys to fumble in a bubble over it. Let's try an example together. Calculate the oxidation state of phosphorus in P4O10. Let's go. This is a neutral species, so the oxidation state is equal to 0, the sum of it. Phosphorus is the unknown, right? So this is what? 4x, because we have to take into consideration the number of entities. So it is 4x plus oxygen oxidation state is minus 2. Minus 2 times 10 is what? Minus 20. So 4x minus 20 equals 0. So 4x is equal to positive 20. Divide through by 4, x is equal to positive 5. All understand it? So far, so good. We're grasping. Good, good, good work, good work, good work. So finish off with oxidation number. What we're going to do now, we're going to learn how to use oxidation number to determine when oxidation and reduction occurs. Let's look. So remember, we can term oxidation in different ways. We look on hydrogen and oxygen, We look on the electrons just a while ago. Now we're going to look on oxidation number. If there's a decrease or an increase, chemistry is too easy for you guys to fumble and bubble. Sign up with HTS and stop joking. Let's look. Copper sulfate reacting with zinc to form zinc sulfate and copper. Let's look carefully. We're analyzing each oxidation state. The oxidation state here of copper, right, is plus 2. The oxidation state here of zinc is 0. Why? Because it is uncombined. Remember that rule. The oxidation state here of zinc, however, is plus 2. Why? Sulfate is minus 2. Formula is ZnSO4, so it of course is 2 plus. It's plus 2. Oxidation state of copper over this side, it's uncombined, so it's 0. What is realized happening? Let's look and analyze. The oxidation state of copper would have moved from plus 2 to 0. So there's a reduction in the oxidation state. So because oxidation state decreases, we would then say that copper is reduced. Are you guys seeing what I'm saying? Are you guys seeing it? It's the chemistry now. Wow. Wow. Let's look on zinc. Zinc would move from 0 to +2, right? So because it moved from 0 to +2, it oxidized. There's an increase in oxidation state. You following me? You following?
Yes, sir.
All right, let's look on one more example. Don't finish one. Don't finish
Yes,
one.
sir.
Wow, this is too easy. Oh, people don't love chemistry. Jesus. Chlorine reacting with. Oh my God, chemistry is such a beauty, man. Oh my, I love it. Chlorine reacting with hydrogen to form HCl. Chlorine exists, all gases actually exist diatomically as a diatom in its natural state. So chlorine is going to exist in its natural state. Oxidation state is therefore 0. Remember, hydrogen is oxidation state is what? +1, except in hydride. This is not an hydride. So this is +1. Chlorine charged, right? -1. What you realize? Hydrogen, well, let's start with chlorine. Chlorine moved from 0 to -1. So there's a decrease in oxidation state. Hence, chlorine is said to be reduced. Hydrogen moved from 0 to +1. Hence, it is said to be oxidized. Is it really that difficult? Redox reaction? Is it? Think about it. Is it? I don't think so. I really don't think so.
No, sir.
It's probably way how you're taught. It's probably, you can look into it, then get back to me. That could be it. Let's just finish off talking about oxidizing agent and reducing agents, right? Now, an oxidizing agent is an agent that causes oxidation, while itself is reduced. So oxidizing agent causes oxidation, while itself is reduced. While a reducing agent, right, causes reduction, right, while itself is oxidized. Let's look at an example and investigate. If copper oxide reacts with hydrogen to produce copper and water, let's look carefully. And we're going to define this in so many ways. I'm just going to play around with chemistry with you now. We're going to show you how chemistry is simple. So we identify oxidizing agent. We're identifying oxidizing agent and reducing agent. So copper here loses an electron. Well, loses oxygen. You realize it was copper oxide, but it's no copper. So because it lost oxygen, we say that it's reduced, right? Because there is a it loses oxygen, which is reduction. That's all. Agree? Copper was bonded with oxygen. Now it's just copper. So it loses oxygen. Everybody agree? Good.
Yes, sir.
Remember, you can define oxidation and reduction in different ways. I'm looking at it now in terms of oxygen. But what if I said to myself, say, you know what, I'm going to look at it in terms of oxidation number. This will move from +2 to 0. So there's a decrease in oxidation state. You see that? So it is reduced. So I've just applied oxygen and oxidation number to show you guys that it still applies to work out to be the same thing. It loses oxygen, which is reduction. It decreases oxidation number, which is reduction. So copper, therefore, is reduced. Now, because copper is reduced, look what it causes now with hydrogen. It causes hydrogen to be oxidized, right? So it causes hydrogen to gain oxygen to become water. So hydrogen is oxidized, hence we can define copper then as being an oxidizing agent because itself is reduced. So we call it an agent of oxidization because it causes oxidization in hydrogen, whilst the hydrogen here causes reduction with the copper because itself is oxidized. Are we following? Isn't chemistry beautiful? And that is it for a redox reaction. You might ask yourself, oh, you don't go through simple redox, different type of redox equation, not different type of redox equation, different type of oxidizing substance. I don't teach things that you can go and read on your own. It don't make sense. It's not gonna add any value to you. So you knowing that potassium dichromate and potassium permanganate are known oxidants, you don't need to. I don't need to teach that because that's something that you can go into a book. I teach things that is complex, that needs analysis, that needs interpretation. That's what I teach, right? Pretty much that. But for the persons here that are came on the program, you would have realized that we would have done a lot. I'm not sure if you realize. What have we done? We did atomic structure. We did writing chemical formula. We did balancing equation. We did writing Ionic equation. We did periodic table and trends. We did periodicity. We did acids and base and salts. Did we do something else before that? Salt preparation. And we just did redox equation. We finished 9 topics of module 1 in the space of just a little bit about 2 hours or 3 hours. My 2 senses, if I was you, just think about it. Imagine what you can do if you enroll with more sessions. We're gonna have a 1-day session Sunday for the entire day. Entire day. So they might finish everything. We finished 9 topics. And this is me going moderate. Right? Obviously, if you join the session, I might have to slow down. But I can go at high speed with my students because they're at advanced, they're at good level, yeah? They're a big one in the game. But what I'm trying to show you guys is that we have just gone through a strategy that wins sets. You know, I can't really disclose all of that here because it's really reserved for my set of students like that. You know, you just have to understand. We have some strategy that we work with to gauge persons out to win exams, get the grade 1, get the straight in profile. Last year, we have 5 persons that was placed for chemistry in Cape Chemistry, Cape Unit 1, Unit 2, and CSET in Jamaica, and 1 person in the Caribbean. So obviously, our program works. All right. Good. But simply put, it shows that we go through 9 topics in section in less than 3 hours. So the whole day session, I never know. You have about a month and a half to make a conscious decision. You have to remember, guys, and when I post in the group the other day, I get a lot of backlash, right? I know that a lot of you guys are here right now that probably would have been, oh, this one all about money and blah, blah, blah. And I'm not about it. I'm not. I'm all about, I know that chemistry is a very tough subject. And I'm all about influencing and changing lives. Yes, Eddie and them cuss me off. This guy love money, blah, blah, blah.